Oh, it's okay. Yes. Tu vas présenter ou tu peux présenter toi?
So, hello everyone. For everybody who doesn't know me, I'm Manuel. So I'm a postdoc in Innsbruck, and I did my PhD with Tobias Nipke in Munich, one of the heavy Isabelle people. And I've been in the community for about 13 years now. And I've been an editor of the archive of formal proofs for about, I don't know, 7-ish years, I think. And so I'm going to talk about the archive today. And just in advance, I want to clarify that this is basically my view of what the AFP is and what's important about it. And so I don't think I'm going to say anything controversial. So the other editors will probably agree with most of the things that I say, but they might sometimes maybe phrase something differently or put different emphasis. So it's not that this is not like some kind of official AFP presentation that everybody signed off on. Right. So this is the rough overview. So first, we're going to talk about the so-called Isabelle universe. So the AFP and everything that's not the AFP, and how it compares, like what goes where. Then I'm going to talk about the size of the AFP and compare it to other things that are out there that are similar, like LeanMathLab or the COG packages or ROC packages. And then I'm going to talk about the life cycle of a typical AFP entry. So basically what happens, submission, reviewing, etc., maintenance. And then there's some section about technical details, depending on how much time we still have for that. And then some issues and challenges that we face or still face, and then also what's going to happen to Isabelle and the AFP in the future. And I mean, I only have 40 minutes, so some of these things will be a quite rough overview, but I hope to be able to say something interesting that you don't already know yet. Right, so my obligatory what is Isabelle slide. So I presume that most people in here have heard of Isabelle at some point, so I'm just going to give a very short and rough overview, also because it's not that important to talk about all of that if I just want to talk about the AFP. So it's an interactive theorem prover, unsurprisingly, and it's relatively old compared to say Lean. It was set up to be a generic proof assistant in the sense that you can do whatever logic you want in there. It turned out then at the end of the day that almost everyone uses Hall, higher order logic. There's a little bit of work in ZF as well, or some extensions like Hall ZF or Hall CF that I don't know very much about, but basically it's, I would say 95% at least Hall, probably more like 97% Hall. Just because that one turned out to be most usable with the system. This is a fairly simple logic, so it's similar to the logic of Hall 4 or Hall Light and all these other Hall-based systems. There's like a few little tweaks that are not there in Hall Light, but they're like more on the technical side, so they're not super relevant on to a logician, I would say, or to a mathematician. And one of the things that are very good in Isabelle is it has very good automation to take workload off the user, and it has very high performance, very good parallelism. So it was I think it was the first theorem prover to actually have parallelism, like parallel proofs. And another thing is that we try to keep proofs structured, meaning that in lots of our theorem provers, the approach is that you have some goal, and then you hack away at it with tactics. So you kind of write the proof in reverse. You transform your goal into another goal until the goal basically disappears into something trivial. Whereas we usually try to write forward proofs like you would on paper, saying, okay, I showed this fact, which is obvious, and then I derive this other fact from it, and then another fact on top of it until I actually reach my goal. And I put the readable here in quotation marks, because if you like show this to a random mathematician on the street, they will probably say, what is this gibberish? I don't understand any of this. So the readable is, of course, a matter of taste. And I guess maybe some Lean people think that Lean proofs are readable. So it's, as I said, it's a matter of taste. But I would argue that, so we like to say that we have readable structured proofs. And we have a very large library of mathematics. So the biggest focus is analysis, but there's also a bunch of other stuff in there, like number theory and some algebra, etc. So yeah, I'm not going to talk too much about this, but we are relatively proud of that. And Makari's also likes to stress it's not just a theorem prover, but it's a lot more. Like it's a document processing system, and there's like some infrastructure of the archive of formal proofs is sort of part of Isabelle as well. So it's or it's an Isabelle component that you can like load into Isabelle. So it's like a whole ecosystem of software and software components. I think there's even like a MySQL server in there somewhere these days. So it's, if you download the distribution these days, it's like, I think over a gigabyte of stuff. But it's very well polished. So you can basically put it on an arbitrary system and it will just like run without a lot of software. That's very nice. And so okay, now I'm going to talk about the Isabelle universe. So what is Isabelle universe? So the first thing is I have to explain is distribution. So this is what we call the stuff that you get when you download Isabelle. All the theory files, so the theory file is what we call modules in Isabelle, basically all the proof development that you get when you download Isabelle, that's called the distribution. And this contains so-called sessions. So a session is basically just like a bundle of theories, usually that share some common topic. And usually they come, well, the distribution comes with a pre-built image of Pure and Hull, and other images you can build. So it's like an image is basically like a compiled set of theories that you can just use without building them again. So you just like open Isabelle and you load this and it takes like a second or something. Whereas if you were to build it from scratch, it might take a few minutes. And so the most important sessions in there, I would say Pure is basically the most basic stripped down thing upon which everything else is built. And then there's Zermelo-Frankel logic on top of that, which some people use, but not very many. And then the main thing is the Hull logic. And then on top of Hull, there's a bunch of different add-ons in there, like Hull library is just some general purpose library stuff. And algebra is basically our formalization of, what do you call it? Abstract algebra. So there's also Hull computational algebra, so you might wonder what that is. So the reason is that this is one of the places where this more simple logic kind of gets in the way a little bit. So Hull algebra is like the most general way to do algebra in Isabelle, which is what you need if you want to look at, oh, I have a group and now I have a subgroup of that group, etc. And now I want to, like, I don't know, look at some quotient of that. Hull computational algebra is more in the sense of I have a type and that type has like one canonical group structure on it or ring structure or whatever, and this is the one I want to look at, and I don't really care very much about subgroups or subrings of that. So this is typically like if you have things like you have integers and you have natural numbers and you have polynomials and you want to be able to talk about what is the GCD or what is the prime factorization of any of these things without defining it separately for each type. So computational algebra is more like I want to actually compute something. I want to do like computer algebra, whereas Hull algebra is much more abstract. And you can always instantiate any result in Hull algebra for computational algebra. Going the other direction is a lot harder. It can be done, but I usually try to shy away from that sort of thing because it gets very technical and annoying. Yeah, and so Hull analysis is the biggest one of these. I'll talk about a little bit more about that later. Yeah, so this is basically roughly the interesting sessions in the standard library. So yeah, it's like you could also replace distribution with standard library, roughly, I would say. And this is basically curated general purpose library material, meaning that it's not too specialized, so it's of general mathematical interest. And curated just means that, well, to some extent, somebody thought about what is the proper way to do this that is most useful and that works well with the automation, and then did it that way. And the way that this works is it's in a Mercurial repository. So for those of you who don't know Mercurial, it's a lesser known version control system. It's basically like Git, but just slightly different. Very few people have relatively few people have push access to the distribution repository. So I just checked, I didn't check how many people actually have access, but the people who made commits since 2024 was, I think, roughly 15, 16 people. And some of them only made like one or two. So I think there's like 4 or 5 people who make commits very regularly, mostly Macarios, of course. And then there's a bunch of more who occasionally like work on some little part of it. And we don't really have a formal process for soliciting external contributions. So typically what happens sometimes is that someone thinks, oh, like I've been using Isabelle and there's this one fact that I think kind of belongs in the library, or maybe some library lemma is not general enough, or there's an issue with it. And then they post it on the mailing list, and then if they're lucky, then someone who actually has push access will look at it and put it in. Sometimes there's some discussion and we actually don't put it in, but say, well, maybe just put it in the AFP instead of something. But yeah, we don't really have anything like pull requests here, and we will make this a little bit easier in the future. There's some discussion about this, but yeah. So the archive for forward proofs, on the other hand, so this is a different thing. This was created in 2005 by Tobias Nipko and Gavin Klein. And the way it happened was that Tobias visited Gavin in Australia and they were sharing an office, and then Tobias came up with this idea, and then they just like hacked something together. And in the beginning, this was basically just like a static website with handcrafted HTML code, and every time somebody put a new entry in, then somebody like had to make this HTML page by hand and update it. And there was also like no automated testing, but so every time there's like a change or something, you would have to run some builds by hand to see if everything still works. So in the end, this was really like some hacked together experiment. And we were completely unsure whether it would go anywhere, whether anyone would be interested in it at all. Turns out yes, but first of all, like, what were the purposes of this? So I asked them, and basically they said, well, first of all, they just wanted some place where people could, well, first of all, send their proof developments to, and also where they could find other people's proof developments, just see what other people did in Isabelle. And also to be able to see when you develop Isabelle, how do people actually use this thing? Like, do they use it the way that we intended to? Do they do something weird? How well does it work? And also this is also very important still today, if you want to change something about the system, you immediately have this huge test bench of things where you can see what the repercussions of changes are. And yeah, and the intention is also that entries can like import each other and use each other. They do that to some extent, but not very much. So most entries are not imported by anything. So they're more like standalone interesting results and not so much library material. But there are occasional entries that do get imported quite a lot. The license is something reasonably permissive. So the vast majority of them use some BSD style license. I don't really know what that means, but in practice, yeah, you can just do whatever, roughly whatever you need to do with the entry without worrying about it. I don't know how many editors there was in the beginning. I think it was like 3, and then somebody grew to 4, and then I was included, and then it grew quite rapidly in the last few years just because of the workload. And there's also now a technical administrator who takes care of the website and the submission system and everything. We've grown to something like 930 articles now, quite a lot of different authors. Yeah, I just let the numbers speak for themselves. And yeah, there's all kinds of topics. So of course, a lot of mathematics, a lot of computer science, also some logic set theory, even some physics, like stuff about faster than light travel or something like that. Like basically that you can't travel faster than light in relativistic geometry. And also some tooling. So there's also some dedicated tools that, I don't know, define records or prove some stuff that would more traditionally probably be placed in the distribution, but recently there's been a push to also put that sort of stuff in the AFP as well, because why not? Right, so the idea is, why is there a distinction between the two things? So the idea is that the distribution is kind of something very controlled, where we say, this is the standard library, everything works, everything is well thought out, and unless there's a very good reason, there's like only one version of everything. Like there's not 3 different formalizations of the real numbers. There's like one formalization of the real numbers, and that's the one you use. There are like some things, as I said, computational algebra and abstract algebra, where there is some duplication, but there's a good reason for that. On the AFP, on the other hand, is supposed to be more permissive. So there the idea is that anyone who has an interesting formalization should be able to submit it, and it should usually get accepted. So Authors there have a lot of freedom. Basically, they are free to design their entry as they see fit, and basically make decisions on their own. Like basically, we don't tell them once it got accepted, oh, now you have to do it this way, or you have to change this thing. And also the wisdom has shifted a bit. Like in the beginning, there was no AFP, so everything just went into the distribution by default, and some of the stuff is still in there, and kind of nobody uses it or cares about it. So some of these very early experiments. These days, basically the idea is maybe let's not put too much stuff in the distribution, let's just rather put it in the AFP. For example, so one example of the distinction would be that if you show some general theorem from complex analysis that you find in like a textbook, basic textbook about complex analysis, then that should go in the distribution because it's kind of general purpose. But for example, if you have something like the Riemann zeta function, then that's a bit more concrete, and that should probably go in the AFP, and that's exactly the way that we did it. But it's not a very rigid distinction, so we sometimes move stuff from one place to the other place. So for example, the Landau symbols, they initially were in the AFP, and then at some point I discovered that actually I want to do something in the distribution and the analysis formalizations where I kind of need that sort of thing. So we moved it from the AFP to the distribution, and now there is still a Landau symbols AFP entry, but it mainly contains a comment saying, well, this stuff was moved to the distribution, and then I think there's like some extra theorems in there, but the vast majority is now in the distribution. So we cannot delete AFP entries once they're there, but we can basically remove stuff and put it somewhere else, and then just put a comment in there saying that it was moved. Another example would be that the Bernoulli numbers were originally in the distribution in some kind of example directory. They were just like made as some kind of proof of concept at some point to illustrate something, and then I needed them for something, so I asked the author, hey, can I like make an AFP entry out of this? And so that's what we did. Right, so now as for the further terminology, so Macarius, I think, coined this word called the visible Isabelle universe. So that's the distribution and the AFP put together. And then this is something that I coined yesterday. So there's other public projects, big Isabelle projects like SEL4, or the Isafol, which is like a logic formalization in Isabelle, all kinds of stuff about logic. There's ISA4, which is about rewriting and termination analysis in Innsbruck. So these are like very big projects that are completely separate from the AFP, and some of them sometimes move some of their stuff in the AFP eventually, but for the most part, they like to develop stuff by themselves. And then there's also other stuff that we don't really know anything about. So Apple and AWS use quite a bit of Isabelle from what I heard, but they are of course very secretive about it. So I don't really know how much they have and what they have. So these are kind of the three different categories. And when we make changes to Isabelle or to the AFP, then what we do is we look at how does it affect this visible universe. So basically just if we try not to break too many things, and if something breaks, we have to fix it. And if you have a project outside of the visible universe, then this is your problem. So if we break something, then, well, we don't know about it, and you will find out sooner or later, and then it's your responsibility to fix it. And history shows that basically if you have a development that's not in the AFP, then you better be a big company, or well, you better be a company or some kind of research group with an ongoing project or something that works on this, because unless you have very good motivation to keep your stuff up to date with Isabelle, it will probably die due to bit rot sooner or later. So yeah, basically unless you have someone who's very motivated to keep their development up to date, they're not going to do it. And one example of that is Jeremy Abigott had this very impressive formalization of the prime number theorem sometime in 2000, I don't know, 5-ish, 6-ish, 7, I don't know, sometime around that. And basically a few years later, it just wouldn't work with Isabelle anymore, probably even the year after. And every year the situation got worse and worse because, you know, the library changes, etc. And a few years ago, I asked him about it, and he basically said, well, it's basically the state that it's in right now, it's probably not worth repairing it. So, I mean, we have a different proof of the prime number theorem now anyway. And if you still wanted to have the original one, it would probably be less work to just redo it from scratch. Also because the library got much better since then. So they had to basically a big part of their work back then was proving stuff that's now in the library anyway. So yeah, this is just what happens. So the lesson is, please put your stuff in the AFP, because otherwise it will probably break sooner or later. And so as for the size, so it's very difficult to compare the AFP to things like Lean Mathlib or the ROC packages or whatever. Just like I'm still going to attempt some of these comparisons, but I'm just saying that you could always argue that anything that I'm claiming here is unfair in some sense. But I'm still going to try. So I would say that it's arguably the AFP is currently the largest centralized repository of formal proofs, no matter which reasonable metric you apply. So it can be size in compressed megabytes, it can be number of lemmas, it can be number of lines. It would probably all give kind of the same answer. We formalized, so 92 out of Frank Wiedeik's top 100 theorems have been formalized in Isabelle. So not all of them are in the AFP, some of them are also in the distribution, but I think all of them are like in some centralized, let's say somewhere in the visible Isabelle universe. For comparison, yeah, Lean has 82, ROC has 79, so not like super far behind. But yeah, so the size, again, no matter which metric you use, is roughly about 2 to 3 times bigger than Lean's Mathlib. But first of all, Lean is catching up fast. And secondly, well, you could argue Mathlib is mostly mathematics and the AFP is, I don't know, have any exact numbers, but it's probably about like 50% computer sciencey stuff like program analysis stuff. So you could argue that for mathematics, actually, it's maybe roughly the same size. And then, of course, you can argue about details like, oh, maybe like proofs in one systems are just generally bigger than in the other. So the content is still kind of the same or whatever. So as I said, like you can always argue that these comparisons are unfair, but this is just like some numbers. And you can also argue that actually the ROC packages, that's much bigger. The difference is, well, first of all, it's not centralized. And there's like no guarantee that these packages are in any way compatible to one another. And from what I heard, there's also a lot of duplications. Like some of these packages will contain exact copies of the other. Sorry, that's the question.
Yeah, the question.
How do you know the developments in the AFP are compatible with each other if they never import each other?
Well, okay,
rarely import.
That is true. Well, you can. Okay, that is true. You can, in most, I'm pretty sure that you can import both of them at the same time without anything breaking. There are some things that could potentially break, like type class instances, but that's relatively rare, or like duplicate theory names. But we try to avoid that. So in general, that's not really an issue. Of course, you can have incompatibility in the sense that one of them defines some mathematical object in one way and another one defines it in another way. And then if you want to use both of them, you have to translate between them. That can, of course, happen.
Yeah, what I mean by compatible is you can use both of them to do a third thing.
Yeah, that should generally work. So there's some technical things that might potentially break that we're trying to, like, as I said, it could be that, so Isabelle doesn't have qualified theory names, for example. So if I have a theorem called foo and another session also has a theory called foo and I try and import both of them, it's not going to work. And we've been trying to fix that for many years and it will probably happen eventually. But like generally, this is not something that happens very often. So I use the AFP a lot and this kind of stuff happens very rarely. And if it does, then we just like fix it very quickly. Okay. Right, and Fabian Huch's PhD thesis talks about comparison of all these libraries, also the MISA library quite a bit more, and so I don't have too much time here, so I really have to press on. Oh, yeah, so the Isabelle distribution in 2025 has about, so this is just the distribution, right? So this has about 900,000 lines of code, and 90% of that is just whole. And the base whole image has about 123,000 lines of code, and then the whole library is another 70,000 lines of code. And the biggest whole session is whole analysis with another 176,000 lines on top of that. And then the other like whole additions like number theory, I think that's about 20,000 lines. Whereas the AFP has 503,000 lines of code, 5,300 lines of code, and the average AFP entry has about 6,000. The median has about 3,200 with a standard deviation of 9,000. So it's a very like heavily right-skewed distribution with high kurtosis. So what that means is that you have a lot of outliers. So the vast majority of entries have like 2,000 to 3,000 lines of code, something like that. And then you have a few like very big entries. I think the biggest one has like 120,000 lines of code. That's some kind of computer science application. These typically have a very high line number count compared to mathematics. Also because they tend to be more monolithic. Like if you have something mathsy, then you typically break it up into a bunch of different entries that are kind of independent. Whereas if you have some computer science application, then it's often just one very big entry. So about half of the entries have between 1,200 and 7,000 lines. So I think it's fair to say that the typical AFP entry has something like 2,000 to 3,000 lines of code. And another interesting number is that about 60% of the line of code is spent proving stuff, and 20%, maybe surprisingly high, is just dilemma statements, and then 10% is definitions. And also there's not much reuse, as I said earlier, so most entries are never imported by anything. So most entries are kind of like, I would say that there's like two different kinds of formalizations. There's the kind that's like a library that's intended for reuse, and then there's the kind that shows some nice result that you put on your shelf and you display it for everyone to see, but you don't typically intend for other people to use it. And so here's a what happens when somebody who's not a statistician does statistics. So this is basically a histogram that I made of line size distribution of AFP entries, and so it's a log axis, so that's notable to say. And I also put some Gaussian filter on top of it just to make it a little bit more smooth. So, but this is roughly the distribution of line numbers. So as you see, like the majority, the bulk is between 1,000 and 10,000 lines. And then there's like a few very, very short entries, and then there's like a very long tail here that actually goes beyond 100,000. So that just gives you a quick impression. You know what they say about statistics, it's the thought that counts. And then here's the growth of the AFP. I think this is a number of entries. Yes, it is a number of entries. And I don't know how much you can read from this. I guess you can say that in the beginning, well, the rate of growth grew. I don't know if it's exponential, but well, it grew faster and faster. And now it's kind of like reached this kind of steady pace where I think the number of entries we get per year is like, that's stayed roughly constant. So I think it's right now it's about 80, maybe 80 entries per year that we get. And of course, interestingly, not interestingly, but luckily the number of authors also keeps growing. So we keep getting new people as well. So it's not just like old people like me who keep doing all this stuff, no new blood coming along. So the typical life of an AFP entry works like this. So the authors submit their entry. Usually they submit it to the latest release version of the AFP, usually via the submission website. I wanted to show this as well. So like this is the submission website. So put in some metadata, you upload a tarball of your entry and submit it. And what happens then is, so first of all, if you don't want to do this for some reason, you can also send them via email. And also you can, if for some reason you can't submit to the release version, you can also submit to the development branch of the AFP. Sometimes people do that. If, for example, their entry needs stuff that isn't yet in the release version, then you can do that. And there's a sandbox in which these entries get built and tested, and they have to build successfully before you can send them on to the editors. And there's also a linter, which automatically gives style feedback, for example, saying, oh, this pattern here is considered bad style. That's like a brittle proof. Please don't do that. I don't know how many authors actually take that into account, but the editors definitely look at this. And if there's like if it's a reasonable complaint, then they will ask the authors to fix that before they accept the entry. And so these submissions consist of, well, first of all, the theory files, of course, that's like the main content. Then there's a so-called root file, which talks about things like what is the name of the session, what is the timeout in seconds, and also what base session do you want to use. So if you use like a base session that's the right base session, then it might just lead to your thing building faster. So this is basically just for dependency management. Then there's typically some LaTeX code that allows generating a PDF from the entry, which if I have the time, I can show a little bit of that data. And then there's some metadata like who are the authors, what's the abstract, what topic do I consider this to be, to this entry to fall under. And then you can also have, in principle, additional data, like sometimes you have some ML code that does some tooling or some automation. I also have some entries where I use some external SAT solver and then import the SAT proof into Isabelle. So that kind of stuff you could also have in there, but it's relatively rare. Most entries don't have that. And entries can also export data. So sometimes the most typical use case is that you prove some algorithm correct, and then you export some code that's verified correct. And this code you can like basically export, and then it doesn't get stored in the file system, but it gets stored in some kind of virtual file system, and you can retrieve it from the build database afterwards. And yeah, so the way it works, if we get a new submission, then we'll get an email, and then there's a web interface where we can say, okay, I'm going to handle this entry. And sometimes, I don't know, if everyone's busy, then this doesn't happen for a while, but usually like somebody picks it up after a few days. And an important thing to note is that there's no external reviewers most of the time. So typically one editor says, I'm going to handle this entry, and then they review it, and then they decide whether to accept it or not. And it does happen. We have rejected submissions in the past, usually not because of quality, but more like sometimes because of lack of significance, sometimes also because they're out of scope, because generally our requirements are fairly low. So we require honesty. So basically, if you say that you formalized X, then you should have actually formalized X, arguably. And significance, so if you've got a formalization of like 100 lines, it's kind of questionable whether this belongs in the AFP. So we have some submissions that are this short. Typically then the argument is that this is some standard result with a standard name, and so it should go in the AFP. But if it's like just some random thing you came up with, then probably not. And of course, the style guidelines, I already mentioned these. And ideally, you should also have it in a reasonable structure, and you should explain things well. But to the degree to which this is enforced depends on what the editor thinks that that's it. And yeah, the reviewing typically takes a few days, sometimes several weeks. And there's often some back and forth with author, where the editors complain about something and then the authors fix it. But usually at the end of the day, this leads to the entry being accepted. Yeah, so as I said, we don't use external reviewers, and we don't require novelty or significance in the same sense as, for example, a conference or a journal would. And also that we, just by accepting something in the AFP doesn't mean that this is the right or the best way to do it. That's just, we say, okay, this is like an okay way to do it. And we don't even have the time and expertise to really guarantee that this formalization actually does what it says that it does. Like, of course, that's what we want, and we take some length, we go to some lengths to ensure this. But if, I don't know, if Sebastian Guizel submits something about Gromov hyperbolic spaces, then us editors basically will have to say, okay, we'll take your word for it. It looks reasonable. So, right, I mean, we're not like I think none of us are, don't have a PhD in mathematics or anything. So, yeah. So, yeah, the important thing is AFP is not a scientific journal. We see ourselves more like something like Zenodo, where it's a data repository. Usually there's like a journal article or a conference paper that goes along with the entry, and we just kind of see ourselves as, okay, we store the data and make sure that it keeps running. So the important thing is that unlike Zenodo, we make sure that this entry actually works, and we make sure that it continues to work for as long as the AFP exists. Yeah, there's a question?
May I ask, how often do you get a submission? Like, is there a bad backlog of things you need to do?
There's sometimes a bit of a backlog, but it's usually not more than a backlog of like 3 or 4 things, I would say. I would say we get a submission maybe like every week, or sometimes twice a week. Yeah,
Thank you.
okay, I'm really bad on time right now. So how long do I have left?
In principle, 3 minutes so that we can have.
Well, we started late.
We started a bit late.
Yeah.
Let's say 5 more minutes.
Okay, I'm gonna have to skip some stuff, but feel free to talk to me afterwards if you're interested. And the slides are of course all mine. Yeah, so accepted articles are added, blah, blah, blah. Okay, we'll just skip over this a bit more quickly because it's not that interesting. Yeah, so So the AFP uses something called Heptapod, which is similar to like GitLab or GitHub, but it's a more open thing and it works with Mercurial. So that's the main reason why we use it. And the interesting thing is that like once you're an AFP author, you can request push access to the AFP development repository, and you can basically do whatever you want to your entry. And in principle, we require that changes be monotonic. So basically, obviously you shouldn't delete theorems that you proved in future versions. So everything should be like strict generalizations, more theorems, etc. But we don't enforce this. Like nobody looks at this. So yeah, and also in principle, every author can change other people's entries if they feel like it. Of course, the etiquette is that you shouldn't like. You have to do this to some extent. Like if some change you make breaks somebody else's entry, then you have to fix it. But if you do something more substantial, then ideally you should ask permission. Yeah, this is the question.
So I decide to become evil and delete your AFP entry using my push access. Will you discover that? Or
okay, so the question was if somebody were to delete somebody else's AFP entry, would that be discovered? That's a good question. I would imagine it probably gets discovered sooner or later. I mean, and of course, it's all in the history of the repository. But yeah, in principle, I guess you could do that. It would take some time before it would be visible on the main website. It would take until the next release, and it would probably, I think it would probably be noticed, but I'm not sure. It's a good question. So yeah, but I mean, this is very much based on the assumption that people are reasonable, and so far we have disappointed in that regard. Okay, this is not that important. Right, as for maintenance, so there's been continuous integration only for about 10 years now, usually first via Jenkins. And since this year, we now have something called the Isabelle Build Manager, which is much faster. And the build hardware is mostly hosted in Munich. And the way it works is that whenever you push something to the distribution or the AFP, then some build runs and checks whether everything still works. And you can also, if you have some work and you want to check whether it works before you push it, then you can also do that. And people do break the build occasionally, and Macarius yells at them, but it's, yeah, Macarius obviously doesn't like it, but it does happen, and it's usually not a huge issue. So typically people fix it after a few days. And the important thing is that if you break something, then you have to fix it. And usually this happens within a few days. Right, and this works quite well. The price is, of course, that even if you make some tiny change to the distribution, it can break a lot of things in the AFP potentially. So my favorite anecdote of this is that I once made a simplification procedure that check if you have like some assumption that has false in the assumptions, then it gets deleted because that caused some problems if you have something like this in there. So it should be obvious, right? But then it broke about like 20 things in the AFP. And so then I had to fix these. So like even the most obvious small changes you make will probably break something, and then you have to basically make the trade-off. Well, do I want to fix the things that break, or do I just not do the change? But I would argue that this is kind of the only way to do things long-term, because if you expect that any AFP author will indefinitely keep their stuff working with the changes in Isabelle, and that's just unrealistic. Like people leave academia, people die or whatever, so that's just not going to work. Okay, I have to skip over this. Okay, so there's a website which unfortunately I don't have the time to show you. It's just completely statically generated via Hugo, which is a static HTML generation tool. And when we accept a new entry, then we just regenerate this HTML and then publish it. The submission system is implemented in Isabelle Scala. There's some stuff that allows you to have LaTeX in abstracts. And there's also a tool that's integrated into the website where you can search through the metadata, and you can also search for the formal content. So you can like search for a particular constant, like the zeta function or something, and it will find where's relevant formalizations of this. And this search works completely offline, basically. And the interesting thing is that you can also browse through all the theories, and they're completely on the website, and they're all syntax highlighted, and you can like click on theorem names and on constants, and we'll take you through the definition, etc. That's also very useful. Okay, and another interesting data point is that so a few years ago, building the distribution took several hours, sometimes actually even 3 hours. and it was just getting a lot too long. So Fabian Huch and Makarios introduced this Isabelle build manager, which uses some sophisticated heuristics to schedule the builds more better, also for heterogeneous clusters. So before we just had one big build server that did everything. Now we have like a bunch of different machines that were just running around there, and they're distributing them to all of these machines. And all you need is a machine that has SSH access, that you have SSH access to, and then you can like instrument that with the Isabelle build manager. And that's what they do now. And they got the build time for the distribution down to 10 minutes, and for the AFP without the very slow sessions, which is like 2 particular sessions that are extremely slow, to 45 minutes, which is very reasonable. And now you can actually do active development like this. Skip that, it's not this interesting. One big issue is the structure. So anytime you formalize anything, you end up with this discovery that there's stuff that should be in the library, but it isn't. So typically what you see a lot is that if you have an entry, it will have something like a more theory or a library theory, or there's like some lemmas in the entry that are tagged with to do move. And the problem is that moving this stuff actually takes a lot of time, because typically every single lemma in this library goes in a different place in the distribution. And then actually putting it there also takes time, because every time you put something there, you potentially break things because, well, maybe some automation that worked before doesn't anymore. Maybe there's a name clash. So it's not as straightforward as you might think. And also not everyone has push access to the distribution. So So Larry Paulson is very good about this, so he often moves stuff to the distribution, but it's not happening as often as it should. And if this doesn't happen, then the problem is that, well, sometimes you get this phenomenon that some entry imports some completely unrelated other entry just for its library, which is weird. Or even worse, they don't know about this library and they just like basically prove the same library theorems again, and now you have duplication of the AFP. And the worst example of that is the multivariate polynomials entry, which has a lot of its like missing library material spread over half a dozen AFP entries that all kind of import each other now. And if you want to do something with multivariate library polynomials, then you have to know this and import all of these entries. So yeah, the problem is the situation is bad, but it's not bad enough for anyone to actually clean it up. Which is often the case, right? And there's like no grants are getting handed out, no permanent positions are being handed out for people who clean up the AFP. I'm sure you have the same problem in other systems as well. And there's like some refactoring tools on the way by Fabian, for example, to make this easier in the future, hopefully. Okay, this is also not too interesting. As for the future, so the problem is that Larry and Tobias are now both retired. And Tobias's group hosts a lot of the infrastructure and it won't exist for much longer. And Makarios exists, but he's basically like completely independent, like he's not at a university or anything, so he doesn't have institutional resources. Nobody's like, right, there's like no group behind him with money or with infrastructure. So how will this continue? Well, I would say this is a problem that all academic projects have, right? So people retire at some point. There's a lot of there's grant money for publishing papers and doing research. There's not really that much grant money for infrastructure that goes on for decades or for maintaining things, at least not in Germany and Austria. So the idea would be to similar to Lean, create some kind of nonprofit organization and possible source of money. The obvious one is ask companies that use Isabelle. So these exist. The obvious ones are Apple and AWS. They use it quite a lot. But the details are completely unclear. So if you have any suggestions for what to do, then please feel free to tell us. Ideally not me, because I don't know anything about this, but you can talk to Fabian Huch, who's been inquiring about how to get this off the ground. And so, yeah, here's just a long list of acknowledgements of people who are kind of important to Isabelle and the AFP in one way or another. Like especially important for the AFP right now, because otherwise the list would be too long. I'm not going to go through it for lack of time. And then here's a bunch of references about the things that I talked about today. So if you want to read more, then okay, I'm getting Oh, I think my laptop might have run out of battery, so just at the right time. Okay, so yeah, thanks for your attention. And yeah,
Thanks. Thank you very much, Manuel. I think we have time for a couple of quick questions. Yes.
You touched upon this a little bit, but how is typically the burden of maintenance between like the AFP people and the people that wrote the submission in the first place? Like, do you usually fix it, or do they fix it, or do you?
the maintenance burden is typically entirely on whoever breaks it, right? So, I mean, maintenance usually consists of some entry that used to run doesn't run anymore for some reason, and then it's always the responsibility of the person who broke it to fix it. So the people who wrote the entry, I think they do get an email when their entry breaks, but they're basically free to ignore it. If it persists for a long time, then it might be a good idea for them to actually look into it. But I mean, it's unrealistic to expect everyone to do this, right? We have like 600 authors or something, and I don't know how many of them are still active in the community, so it would be unrealistic. So usually if people do change their entries after submission, it's because they want to, because they, for example, want to add some new content to it, or they want to make something more elegant. So it's really just entirely voluntary.
But does it actually work in the sense that, like, so I know from the rock side that sometimes it's hard for the the rock developers to fix people's developments because they were very smart, and like the maintainers don't always have the capabilities needed to fix other people's
That's
developments.
rarely an issue. So usually when stuff breaks, it's because, well, either something trivial like someone renamed a theorem that's explicitly mentioned by name here, and then it's very trivial to fix that. And even that doesn't happen as often, because a lot of the automation in Isabelle relies on kind of implicit theorem collections. Things like the simplifier has the simp set, and everything in the simp set gets used for rewriting automatically. We don't have to mention it by name. So this kind of stuff doesn't really break. What does break a lot is sledgehammer proofs. So especially like in the past, it's gotten a bit better now, but sledgehammer often generates these proofs that are just long calls of the form by Mattis, and then some long list of explicit theorems like, oh, adding 0 to x equals x. And so that kind of stuff tends to break more often, because you've got all these like obscure library theorems that nobody ever mentions by name, because they disappear automatically if you call auto. So that is more brittle. But Sledgehammer's gotten better about this, so it doesn't always generate Mattis calls now. It often also just generates by auto simp blah blah blah, and then that works a lot better. And so other causes of breakage, they do happen, but usually we're able to fix it without asking the authors, I would say.
And without understanding the mathematical content of
Exactly,
the
yeah.
entry.
Often what you also just do is, if you're really stuck, you just delete the proof that's there and you run Sledgehammer and it just finds a new one. because like we have these structured proofs, right? So it's not like we have some big monolithic proof, but we have like, okay, now I have this fact from this other fact, and then I have this fact. So the step from one fact to the next one is typically very small enough that you can just handle it with a single Sledgehammer call or something. And so I would say that if you do structured proofs, you typically, the actual like tactic invocations that you see, they're not like 10 tactics in a row, but they're like 1 or 2 tactics, usually something like by auto and some additional facts, or maybe some by apply this substitution, unfold these definitions, and then run auto. And that's it. So, and in particular, we also don't really, like, we mostly use general purpose automation like auto. We don't have like 10,000 tactics that do one very specific thing that you have to understand, and only in one, if the goal has exactly the right form, but really just like, you know, these are the facts, deal with it.
Is there another question? Yes.
Yes, little user-defined automation then? I mean, apart from calling auto.
Yeah, I don't think there's much user-defined automation. So you can do it. There's this thing called Eisbach. That's kind of an inside joke. So the Isar, the proof language of Isabelle is called Isar, and there's like a small brook in Munich that flows into the Isar, which is called the Eisbach, and so that's why it was called Eisbach. So that's kind of like a small proof, like a small tactic language, or you could say, or method language, which allows you to construct automation without writing any ML code. So that gets used to some extent. And to some extent, people also just write their own ML code for automation. And as I mentioned, so some AFP entries have their own ML code to either like prove a bunch of facts in bulk or to define their own tactics, but it's relatively rare, I would say, like probably less than 5%. So I do this quite a lot, but even my AFP entries maybe like 5% at most have this. Yeah, so and generally, as I said, there's not that much special purpose automation. There's like some automation to deal with things like algebra, like Rubner basis stuff, and then there's some automation to deal with things like proving that something holds in all measure spaces, like so inequalities or distances, or proving that something holds in about orders. And of course, the real asymptotic, which I think a lot of people know, which I wrote, which proves real limits. But that's kind of the exception. And even these, a lot of people don't know about them and don't use them. So for the most part, you're fine just using things like SIP and auto.
Okay, thanks again, Manuel. Do you have your computer here?